Yeah, so today I'll be talking about building a trusted system in a time of crisis, indeed. And I was going to break that down into these five sort of categories. So a very quick intro to faculty, which is where I work. Again, very quick context on the NHS, the UK's National Health Service. And sort of how the COVID crisis kind of hit them, and then I'll sort of zoom out and talk about the technical challenge at a very high level, because this sort of the NHS's response to COVID is actually just an example of a kind of broader topic, and then zoom back in, talk about the technical approach and the impact. So jumping right in, very brief intro to faculty. Faculty is a UK-based AI company, and we build the intelligence layer for organizations. So sort of sits on top of derived data to kind of convert into decision-making across an organization. So there's a little graphic on the left, but I don't actually want to spend too much time of this group on faculty. So I'll rather give what is hopefully a slightly more interesting angle, which is sort of how we think about these types of problems. So we have a kind of a big research lab and really try to be at the forefront of machine learning technology, but also integrate that into businesses in essentially a partially bespoke manner. So we kind of sit in between, like what a consultancy would do, where they start from scratch and do something really bespoke, which has upsides and downsides. And for example, what like AWS would do, where they kind of create a very good, scalable technology, but very sort of one size fits all. So that's how we think about these things. And then to sort of give an example on the research grade side, and then the rest of my talk is going to be about actually the kind of the system build for the NHS. We've focused quite heavily on trusted systems. So here are some examples of explainability research that we've done, and one in particular is very relevant for the COVID response that I'll be talking about, is this asymmetric Shapley values. In case you want to just Google it, it's basically how to incorporate causality into the Shapley value framework for explaining AI systems, and it is totally necessary in our experience. This technique for explaining Bayesian forecasts, which you'll see a little bit later. And what is just kind of cool, obviously I'm proud of this, is this technology was kind of deployed in the NHS in the summer of 2020, 6 months before it was presented at NeurIPS. So we kind of very much try to get these things into the real world, as well as the sort of academic literature. So that is all I'll say about faculty. I didn't want to spend too much time on that. And let me do a similar, very quick setup for the NHS context. And indeed quick, because like we all know about COVID. So these are the UK numbers. So the UK has had so far about 8.6 million positive tests, and about 560,000 patients admitted to hospital with COVID, and that is unprecedented, clearly. And this actually required just a completely unprecedented response in the healthcare system, because epidemics move so fast. You have to operate as an organization in a different way. And so this actually precipitated a sort of very significant data and algorithmic kind of system builds, so that you could bring the planning cycle down from months to like days, and it just like there was no other way, which was sort of daunting, and definitely exciting. And so we, as part of that, we were brought in, partner with the NHS to provide basically a forward-looking, risk-adjusted view of demand across the health system. So think forecasts for all the kind of critical medical metrics, like how much oxygen is needed, how many ventilators and stuff like that, for every single hospital across the system, and then also turning that into the sort of the crisp operational decisions, like moving things around and so on. So that is a sort of ultra quick run through. I want to spend more of my time here and on the approach. I hope that's helpful for this audience. So let me now zoom out and just talk about the technical challenge. Talk about the technical challenge in general. So this kind of NHS COVID response was just like an operational planning problem in like an extreme context. But operational planning is hard for organizations, even when not in a crisis. So these are kind of the three main shortcomings that organizations face in their like operational planning functions. So poor performance, forecasts and models that basically don't sufficiently correspond to what actually happens. Low confidence. So even if you had a good forecast or a good scenario, people have no idea where it comes from, or whether or not they should use it in any particular way. And then all of that kind of coming together into very reactive decision making. And like that's true even in a time that not in a crisis. And we may think that COVID is mostly over, so we're back to not in a crisis, but that's clearly not true. I'm sure everyone has seen like 1,000 articles about supply chain shortages in the last couple months. It's basically global. It's got to the point where like the articles are now getting boring and like the cartoons are coming out, which seems like a sort of standard news cycle. But anyway, here's an appropriate supply chain cartoon I found. So operational planning is really important, and it's really, really hard. But you hopefully are thinking perfect for AI, and indeed, I think operational planning is ripe for disruption due to AI. So a lot of organizations, when I say poor performance, like this is roughly the level that it's at. Like very simple forecasts, like in some cases, like backwards looking averages, or last 6 months is what's going to happen in the next 6 months, type forecast. Also, a lot of these models, in cases where they are models, are over reliant on a single metric. So like demand for a given product is just an extrapolation of the time series of historical purchasing of that product. So rather than using a bunch of different data sources that all sort of like are leading indicators to demand or something. And of course, insufficient granularity for operational decisions. When you need to make operational decisions, you often need to like know how many of a given type of screw you're going to need, like to build a product, or like a medical hose or pipe. These are really, really, really granular requirements. And so this is clearly ripe for, or hopefully this sounds, ripe for disruption due to AI. But let me maybe just like temper that a little bit and say, the technical solution isn't sort of the cavalier, train a deep learning model and we've solved it. Indeed, deep learning has not revolutionized time series forecasting in the same way that it has computer vision or NLP. Forecasting is almost a qualitative, like it's a qualitatively different problem. It's kind of extrapolation rather than interpolation, which is one of the reasons why some of the best models tend to be these like simple statistical models, rather than black box, really high capacity deep learning models. And then like a third reason why the problem of forecasting is actually quite a bit different is that time series data just tends to be less, copious. Partially because the relevance of data basically fades over time. Also, like a lot of time series are very seasonal, and if you have like a long-term seasonal effect, like let's just say Christmas, if you look at the last 3 years of data, you've got 3 Christmases, and each one essentially is totally different because it was like no COVID, full panic COVID, and then like this upcoming Christmas is presumably going to be somewhere in the middle or totally different. Who knows? So it's kind of a different problem than your sort of traditional machine learning problem. So that's performance. Then again, there's sort of two other categories that I wanted to go through. So there's low confidence. So a lot of the time, because you're trying to get so granular, the actual thing you're trying to predict is just incredibly volatile. It's like almost all noise with a very weak signal in it, and that can make a sort of naive or a sort of point-wise forecast operationally kind of useless. Another reason is the people who are taking the like outputs of these models are not, statisticians. They're operators of various types. So the kind of the imperative to know why a forecast was what it was, or what drove the forecast is actually really high. A person's not going to sort of like understand, well, it's a Bayesian hierarchical model using a zero inflated Poisson or something like that. Just it doesn't really work. And then a last one, which just adds complexity, is that there are forecasts of what you think is going to happen, and then there's like the plan that you want to take, like the actions you want to do. So you might say it's most likely, the following thing will happen, but I don't want to plan for the most likely scenario. I want to plan like much more conservatively. So kind of there is some translation between sort of unbiased forecasting and what an organization wants to do. So that's the second sort of. Oh, actually, no, sorry. Those are the issues with low confidence. And again, it's not completely trivial, the technical solution here. So with very high volatility, Bayesian methods are great because you're sort of forecasting, the whole sort of uncertainty distribution of what might happen. But obviously they're computationally demanding and so on. In terms of ability to understand the forecast, like even these like simple statistical models are actually not interpretable, even though they might be based on like underlying linear dynamics, and sort of similarly for converting forecasts into actions. So last bucket before I kind of jump into the technical solution is like turning these things into decisions. So there's, in the kind of current world, some of the challenges are things like very siloed planning. So you have a bunch of teams that like don't really talk to each other, and so or optimization within an organization is like done by human minds in a very greedy way. So each different team does what they think is optimal, and that is not at all necessarily optimal across the value chain. And there's a kind of a number of other challenges that I think I sort of won't belabor. But the technical solution here again it's not super easy. It basically, you need the very good technology that solves sort of the performance and the confidence stuff that I just talked about. But you then need to like build it bespokely into an organization to overcome the silo problems. And so that is indeed like it's sort of an inconvenient duality because, most organizations that are like really good at, solving the technical problems don't really want to spend their time sort of bespokely integrating a machine learning system. So how do we overcome this? So we need state-of-the-art performance. We need to be able to build confidence in the system for non-technical users, and we need to somehow bring this all together to support proactive decision making in complex organizations. So let's see how we did this for the NHS. So I tried to distill it as much as I can. You'll sort of see as I go through the details. But here are maybe the kind of four main sort of elements. Bayesian hierarchical forecasting. You'll sort of see how important that is. That's sort of the underlying statistical model. Explainability. So every single forecast needs to have an accompanied explanation. And this actually, as like to the best of my knowledge, only makes sense to be explained in this sort of asymmetric Shapley values context, which I referenced at the beginning of the talk. And then you need like automated pipelines or pipeline monitoring, to build trust with end users. So end users like actually can go see what forecast was in the past, how it performed, and get some intuition for how these models work. And then of course, sort of full integration into decision-making processes. So let's go through these in a little bit of detail. So starting with performance, there's basically three kind of main elements here. So expert knowledge, maybe going back to this interpolation versus extrapolation point. Expert knowledge is super important. So we built this. The underlying statistical model are based on Richard's curves or sort of generalized logistic curves, which like approximate solutions to the like epidemiological differential equations from like SCIR models. So you've got a statistical model that is built on sort of curve fitting for an epidemic. Like that is basically a bespoke model, right? You're not going to use that to predict, A&E or urgent care admissions, for example. So that's kind of one component. The second, which I'm not going to spend any time on in this talk because it's sort of just there's a lot of detail here, is being able to pipe in a bunch of leading indicator data as well, like testing data and cell phone or mobility data to see when people are kind of bumping into each other in the parks and in restaurants and so on. And then in order to get to kind of the hospital level across every single metrics, full granularity, but in a way that is still like data efficient and performant, we used a hierarchical model. So this is, Bayesian hierarchical modeling that I referenced before. And let me just give an example quickly of why that's powerful. So in the plot on the right, there's just three forecasts for three different hospitals, which have sort of different, the sort of epidemic wave hits at different times. So hospital 1, it hits early. Hospital 2, it hits a bit later. Hospital 3, it hits after the above two. And the blue like little crosses are the actual data, and then the like gray dots are what happened in the future. So think of this as a post kind of post validation of the forecast. The forecasts were only trained on the blue crosses. So because one hospital has gone through a COVID wave, essentially fully, when you go to a forecast for hospital 2, which is just like a sort of noisy uptick, you're actually able to know, roughly what that turnover is going to look like. And even for hospital 3, where you've only got a couple data points, like you're missing tons of data, and it's just starting, you basically get a decent forecast. The sort of confidence intervals are maybe a little bit too big, but a decent forecast despite having almost no signal, because you've seen a bunch of other hospitals already go through the wave. So this gives you, actually a kind of incredible amount of performance given the kind of the amount of data you had on hospital 3. So that's sort of how to get the performance of the system. And then in terms of confidence, I've mentioned explainability a few times. This is a sort of actual kind of screenshot of an explanation of a forecast. Every single forecast in the system just have like explain this forecast button, which pulls up a very simple table like this. So, each row in this table is one of the inputs. So like, hospital admissions 3 weeks ago. And then it just gives a percent impact that it had on the forecast. And then like a pros table that like tells you about it in pros. And then you can obviously click and view the underlying data. This is like super, super simple. And the reason is because, users of the system aren't statisticians, they're hospital operators. And under the hood is like this NeurIPS paper, but nobody needs to know that. So it's just kind of put together in a nice little table. So a few other things which I think, just for the sake of time, I'll probably skip. But confidence intervals like play a huge part. This is super uncertain forecasting. These epidemic waves are come really fast. So obviously confidence intervals just help not over anchor people to the wrong answer. And then every single user of the system just has like full transparent access to the historical performance. So here are a couple sort of screenshots of the performance tab. So at the top, you've got like over the last 6 weeks for each hospital, these bands are the credibility intervals, like straightened at the top, and that's just the actual data where it landed. So it just like gives you just an intuitive idea of how calibrated the forecasts were, where the data landed. The bar charts underneath are for the 50th credibility interval. How much data landed within it. Most of these bars are like 50 or 51% of the data landed in the 50th, 80 or 81 or 82% of the data landed within the 80th, and then 95th. And then at the bottom, you can actually just like dial back time and look at what the forecast looked like, 3 months ago. Now the data is accrued, so you can just see how it performed relative to data. So here's just a bunch of different. These are just the 95th confidence intervals at like 6 points in the past. Lastly, decision making. So these kind of Bayesian models are super important. So a sort of a point-wise forecast is like, I'm going to need 30 beds in in 2 weeks' time. So that's just this like whole vertical line. And the histogram is the Bayesian posterior. I'm going to need, this many beds. Well, this is the probability distribution of the beds that I'm going to need. And that is very important because you want to make decisions like how many beds should I hold back for COVID patients? So you could hold 30 beds and you've got a 50% chance that you run out. So the red on the histogram, is the probability of running out. Or you could hold 40 beds and you will have a sort of 5% chance of running out. And you can just immediately make that decision. So with the point-wise forecast, you can't like reason about these things. Whereas with the posterior, you can just say, what probability of running out do you want to have? And of course, that comes at a trade-off. If you're most likely going to hold 10 extra beds that are going to be empty. But that's worth it to have the lower risk, perhaps. Kind of depends on what matters. And you can go even further, but I actually won't spend any time on this. So let me just wrap up and quickly say the kind of the impact here. The tangible thing is probably just that hundreds of NHS staff are using the system every day. But sort of more specifically, there's just been kind of a clear shift in how the NHS makes critical decisions. So ability to respond in real time, having the confidence to just schedule elective care. Even people worried about COVID, they now can like quantify that concern and keep doing like breast cancer screenings, even though they're worried that they might have to, that COVID might flare up. And the NHS is now using this technique for non-COVID stuff as well, like urgent care. Cool. I will wrap up there. I see I'm well, maybe less than a minute over time.